Hello, my name is Sarah Petersen. I am a PhD student at the University of Notre Dame, and my advisor is Mark Behrens. My research focuses on computations in equivariant homotopy theory, and in my thesis, I investigate multiplicative structures in order to compute the ROC2 graded homology of C2 equivariant Eilenberg-MacLane spaces. Non-equivariantly, this computation was completed by Sarah in the 1950s. However, additional structures in the equivariant setting make direct extension of these classical techniques difficult. For this reason, I would like to begin by describing the Hopf ring methods that motivate my approach to equivariant computations. First, recall that a Hopf ring is an object in the category of graded co-unital, co-associative, co-commutative coalgebras. And as such, one consists of a sequence of abelian groups, M sub I, together with a coproduct and graded multiplication, here denoted with the circle product. One place Hopf rings arise in homotopy theory is in the study of omega spectra. So consider an omega spectrum G. This represents a generalized cohomology theory, with the cohomology of a space X being equivalent to the homotopy classes of maps from X into G. And since the cohomology group GK of X is abelian, the space GK will have a commutative multiplication in the homotopy category. In particular, this H space structure, denoted with a star, gives rise to a product in homology. If we require that our homology have a Kunith isomorphism for the spaces GK, making the E homology of GK a coalgebra, then the E homology of G will have the structure of a Hopf algebra. If we have additional structure and G is a ring spectrum, then the cohomology of a space X is a graded ring, and this corresponds to a graded multiplication on the spaces of the spectrum. Applying E homology, we get a circle product, making the E homology of G a Hopf ring. So an idea pursued by Ravenel and Wilson was to use these two products, the star and circle product, to produce many elements in homology from just a few. And they successfully applied this approach to compute the mod P homology of classical Eilenberg-MacLane spaces, the Hopf ring for complex cobordism, and the Morava-K theory of Eilenberg-MacLane spaces. Given that these products describe so much structure non-equivariantly, it is a natural question to ask if additional computational leverage can be gained by studying them in the equivariant setting. To discuss this, we'll begin by recalling some foundations of equivariant homotopy theory, in particular ROG-graded homology. So here, we let G be a finite group and V a real representation of G, and we consider representation spheres, SV, which are the one-point compactification of V. We then grade our cohomology on the real representation ring of G, allowing for a suspension isomorphism for all of these spheres SV. In the particular case where G is C2, the cyclic group of order 2, we have two irreducible representations, the one-dimensional trivial representation and the sign representation, also commonly denoted sigma. We then grade our homology on these two representations and take coefficients in F2, the constant Mackey functor, which is an equivariant analog of the group F2. We also have an Eilenberg-MacLane spectrum for the C2 constant Mackey functor, and we denote the spaces of this spectrum KB. Up to C2 equivariant homotopy, HF2 is characterized by the cohomology of a space being equivalent to the homotopy classes of maps from X into KB, giving us a notion of the star product. Additionally, HF2 is a genuine equivariant ring spectrum, and for this reason, we also have a circle product. In my work, I give explicit models for the star and circle product on these equivariant Eilenberg-MacLane spaces KB. I used the bar and twisted bar constructions to do this, extending non-equivariant work due to Ravenel and Wilson. I also investigate the ROC2 graded bar and twisted bar spectral sequences, recovering computations of the homology of K sigma and K z rho, where z is the constant Mackey functor and rho is the regular C2 representation. I additionally compute the homology of z2 sigma using the twisted bar spectral sequence. However, when applying the twisted bar spectral sequence to compute the homology of other Eilenberg-MacLane spaces, for example, K2 sigma, I find that there are arbitrarily long equivariant degree shifting differentials. And for this reason, I opt to take another approach to completing this computation. In particular, I use a lemma due to Mark Behrens and Dylan-Wilson. And this lemma says that if we have a C2 spectrum X and a collection of elements B sub I in the homology of X, such that these form a basis for the homology of the underlying space, as well as a basis for the homology of the geometric fixed points, then the original ROC2 graded homology of X that we're interested in is free over the homology of a point, and moreover, these elements beta sub I form a basis. So given this lemma, my computational strategy was to start with the homology of some spaces we know, so for instance, K1 and K sigma, and then use circle products to produce elements in the ROC2 graded homology of KB. I then use my explicit models for the star and circle product to analyze the maps to the underlying and fixed points. This allows me to use the Behrens-Wilson lemma directly. To give a flavor of these answers, we'll describe the homology of K sigma. So here we let E sigma be in degree sigma and alpha bar I be in degree rho I. Then the generators of the ROC2 graded homology of K sigma are E sigma and alpha bar parentheses I in degree 2 to the I rho. This space additionally has a coproduct formula, which also includes elements shifted by the distinguished elements A and U in the homology of a point. Given the homology of K sigma, we can write down the homology of Kn sigma by taking finite sequences of non-negative integers and defining circle products involving E sigma and alpha bar parentheses I for all of these sequences. I then show that the homology of these spaces is exterior on these generators. Interestingly, this answer mirrors the non-equivariant Hopf answer for the prime 2. To give some idea of what happens when we also have a trivial representation, we'll write the homology of K-rho. To write this down requires additional generators, beta sub I living in the rho I homology of Kz rho. And this gives additional generators, beta bar parentheses I in degree 2 to the I rho. I then show that the homology of K-rho is exterior on circle products of elements in K1, K sigma, and K-rho. So some future and current directions for this work include using these answers given in terms of circle products to understand the differentials and extensions in the twisted bar spectral sequence, potentially aiming for a refinement of the E2 page in terms of twisted homotor. Additionally, I'm interested in pursuing equivariant analogues of other Ravenel-Wilson computations, including the real Morava K theory of C2 equivariant Eilenberg-MacLane spaces, the ROC2 graded homology of the spaces of the real Brown-Petersen spectrum, and the ROCP graded homology of CP equivariant Eilenberg-MacLane spaces. Here are some references for different works that I've mentioned, and thank you for watching.